Okay. Any questions before we start? By the way, there is discussion that goes on the forum. More than 47% of you don't participate, if you get my drift, but you should. Okay. And I think some people actually are taking part, and I think it's you can get more in terms of the topics being discussed if you also follow those a little bit. Okay. By the way, these were the questions that I suggested, but nobody else is asking anything specific. I think there was some interesting question that Kaushik asked at the end of last class, and that's discussed in terms of the issue of what exactly is the distinction between having a simulator versus having a model. You know, I think these are some of these are certain issues, and so it's worth thinking about them. And if you have a question, you probably have a good question. Okay. So I think you can follow some of that. He summarized, and then when we discussed after the class, he summarized it, and then I gave some sort of an extension on top of his summary, and that's worthwhile, possibly. And then you can ask me questions on that. Anything else? You didn't ask me any questions, but okay. So if you don't have any questions, then I'm going to continue the discussion of reinforcement learning. Today will actually be the last class on reinforcement learning. The way I'm planning to do it actually is that I am considering reinforcement learning at the atomic level. That's what we'll do by the end of today's class. And then we can also talk about reinforcement learning at factored level. That means essentially states are represented in terms of some state variables, and value function is some function over those state variables. And so, in fact, most of what you're doing would be, the learning would then be in terms of changing the weights of those features in computing the value. Okay, so right now, in all the work all the discussion we have been doing, we're just assuming V of S1 is a quantity to be directly learned. Okay, and that's what I'll stick to right now. But eventually, we realize that all states S may actually be represented in terms of features 1 to n, some state variables. Okay, and then maybe you want to act as if the value of the state is W1 F1 plus W2 F2, etc. Wn Fn. Okay, and that would be the value function. Then essentially, when you are when in the normal reinforcement learning, you have an estimate of the value of S1, and then you update it to become closer to the real value of S1. Okay, the same thing you do here, except now the value is actually itself written in terms of the features and their weights. And so rather than just update the value directly, you update the weights. Okay, that's what happens in factored reinforcement learning. And that connects directly to, that's what I mentioned, for example, in one of the slides that I mentioned quickly last time. So you basically, you do inductive learning. You get, essentially, you are being told that previously you thought the value of the state is, let's say 19. Now you are told that the value of the state should be changed to 21. The question is, how do you change these weights? You know the features of the state because it's a fully observable case. So how do you change these weights such that now it adds up to 21? Okay, and that's essentially sort of an inductive learning problem. And we'll get to that, at some point of time. Because in general, we haven't talked about how to do MDPs with factored approaches, in factored representations either. Okay, so I'm trying to understand everything at the atomic and then come back to the factor. So in the text, on the other hand, if you basically go a few more pages after where we stop today, they will already start talking about this weight learning, for example. And that's the point. Basically, they're learning, they're updating the value function by updating something underlying. You know, they're making a big assumption that the value function can be written in terms of some function of the features. And they're also making an assumption as to what the form of that function would be. They're assuming, for example, it's a linear function. And then they're computing those weights. Okay? But anyway, so we would not do that right now. We'll come back to it at some point of time. But by today, mostly what I'm planning to do is, so last time we were just talking about passive reinforcement learning, and then passive model-based versus model-free versus model-based. So we talked about Monte Carlo, which is model-free or model-based.
Model-free.
Yes, model-free. If you don't learn T, then it's model-free. That's it, right? And then we talked about ADP, which is adaptive dynamic programming, which is essentially passive ADP, where you first learn the T and then convert it into pi, and convert it to V. Okay, and that's model-based. Okay, and then we started talking about active learning. And then when we were talking about active learning, then we realized that active model-based learning, okay, and we realized that essentially we need to be careful about doing some exploration, because if you don't do exploration, we would not be guaranteed to, converge to the optimal value function. And that's what we were talking about when we left last class, that if you start with a policy and you just start doing reinforcement learning from there, it's possible that you would not ever go into certain huge stretches of the state space. And again, as I said, in one of the questions that I was asking in the forum is, why is this a problem here, but not a problem for policy iteration, where too you started with an arbitrary initial policy. Yeah, and then that is, you should make sure that you understand, yeah.
So, obviously that was answered on the forums, but would that be that we have a complete understanding of the reward function?
It's not just the reward function. You have a complete T. In policy iteration, you have the complete T, complete model. Okay, and here you only have, so the point is, if you start with this as the initial policy, then you will never learn the parts of the T which will involve these states at all. Not just, you already are noticing that you won't learn their rewards, but neither would you learn the parts of the T that will get you there. That's the problem, ultimately. Okay, so MDPs are pure inference. So here is another very interesting point to keep in mind. When we learned MDPs, we did pure inference over complete models. Okay? Reinforcement learning actually sort of combines inference and learning. Whenever it's learning a new T, it's a learning aspect. And it converts the T into a pile, it's doing inference. And in real life, that's what happens. You have some understanding of, when I say you have some knowledge, it means you have some knowledge about the T and R functions. Using that knowledge of T and R functions, you can do inference to figure out what your best plan is. And then you start acting with it, and while you're acting with it, if you throw in some exploration, you will basically learn a better approximation to the T and the R functions. Now you do inference over those, then you get a better plan. So reinforcement learning is planning and learning combined in one, nice big block. Okay, it's that sort of, you keep improving your model as well as doing planning with it. So pure inference part is just planning. That's what we are talking about. So we assume that the model is being given. Okay. So we mentioned at the end of last class that basically you do need some exploration component. In particular, you need something which in the end it becomes greedy, but you have to essentially ensure that every state action pair has been infinitely explored, so that you will get every possible unlikely transition of an action will still be found. Do you understand what I'm saying? Suppose there's a particular action that you're doing which has 10 power minus 7 probability that it will bring the world to an end. Okay, so you tried this action a couple of times. Unless you are like the most bad luck Brian out there, you won't get the world ending in those two instances. That doesn't mean that that doesn't exist. If I gave you the full model, I would have given you 10 power minus 7 possibility that the world will end. And then to the extent world ending is like a big deal to you, you might decide not to do actions that will lead to that. Okay? Whereas since you are learning the transition function by actually acting out, doing this action in that state, you better do it infinitely often so that you will get all the probabilities correct. Do you see what I'm saying? So that's why you sort of think in terms of greedy exploration, greedy in the limit of infinite exploration. So in the beginning, you essentially want to, this was, we were discussing last time too, in the beginning you want, at the minimum you want to do the following thing. You want to say that with the 1 minus epsilon probability, you act according to the current greedy policy, and epsilon probability you do a random action. And I also mentioned this epsilon can be changed to be smaller and smaller as time goes on. Okay? And then furthermore, I mentioned even better idea, which is this epsilon changing essentially says, at any given time from any possible state, you have the same probability of doing the random action versus doing the greedy action. Greedy action is with respect to the greedy policy. Okay, but what you might want to know is if this particular state action pair has been already seen 10,000 times, then probably you know enough, as much as there is to know about that. Whereas some other state action pair has only been done 2 times, it requires a lot more exploration. So what you really want to do is throw in exploration that is sort of connected to the individual state action pair trials. Okay, if you have tried it enough number of times, then become less explorative. Okay, if you haven't tried it enough number of times, then give a higher probability of doing the random action, which makes a lot of sense. Okay, and so here is an exploration function of that kind. Essentially, think of a function f to be defined this way, where f of u and the number of trials, it will take the number of trials on the current utility and it will give you u plus k by n. Okay, where in essence, the number of trials, as the number of trials increases, this factor becomes 0. In the beginning, you are essentially adding novelty factor for state action pairs that haven't been explored enough. Do people see that? Okay. So that, if you have, that's just one form. In anything which as n increases, as the number of times you tried that state action pair, if that count increases, if this factor becomes close to 0, or in fact, in particular, as n tends to infinity, the f of u of n, f of un becomes just u, you're fine. Okay, and this is one such function. And then in essence, to get the effect that I'm asking for, what you will essentially do is you set the value function, u, not in terms of just the normal u that you compute, but in terms of this u plus, okay, where u plus is f of the utility. Okay, and I just now wrote in this case, I'm basically setting u plus of s in terms of the reward from s plus the backed up reward appropriately scaled using the f function, which will be actually the true backed up reward if NSA is large enough. Because if NSA is large enough, f of this and this will just be this. Right? So that's a way, if you do this, if you do this backup, then in essence, you are going to be exploring the state space with the right type of behavior. You will explore certain the states that, where the states that, basically this f function is going to add some value to states, make them look more enticing to the underlying, Bellman backup, just by artificially increasing their value. Do you see what I'm saying? Okay, so you make the new thing more, it's because all the decisions are made only in terms of the u function. So instead of searching in terms of the normal value function, so instead of searching in terms of the normal value function, you search in terms of u plus function, which basically has this property that it makes the states that are not, state action pairs that are not being seen yet, be more enticing. Yes?
What was the k in that, the definition of?
This is just k is the maximum I am adding. So when n equal to 1, basically you get k amount of extra. So it's like everybody, anything that hasn't been tried gets like k units of reward, k units of long-term value, so that you will try it. But it's been tried, then it's true. So in fact, I just want to tempt you to try it. After you try it, then you'll actually figure out what its true value is. And then that's what you will remember. So k is just an arbitrary constant. What?
We'll need to do 10 to fit MVP or on, right? If the reward's 10,000 already.
Yeah. But it's basically the point is this is the amount that you're adding. So if you make k to be much larger than the R max, then in essence you are saying everything new is way more interesting. So it takes a long time for the reinforcement learner to actually be greedy about the knowledge it's learning. Okay, so again, these words, things like being greedy about knowledge you are learning, essentially means you're taking the current transition function and you are actually acting as if that is the final transition function, and you're taking the greedy policy with respect to that. You're computing the value and then computing the greedy policy with respect. Okay, so that's about exploration. Any questions on that? Any further questions? So now we have done the following. We've done model-free learning in the beginning because we did Monte Carlo. Then you did model-based learning, passive. So model-free passive, model-based passive, then model-based active. Which now means I need to still do model-free active. Okay, so in fact, actually, let's talk about model freeness once more. We mentioned it in the background last time, but essentially the idea of model free learning is learn the value of a policy, in which case you're doing passive, or the very best policy, optimal policy, in which case you're talking about active reinforcement learning, without bothering to learn the transition function. Once again, it's possible to do this, and you need to understand why would anybody want to do it. I'm giving you some motivations. For example, in some cases, T is just too big. T is just too big. Okay? And it's easiest to learn what's the right action to do than learn the transition function. My question that I had in the forum was, do you think, to the extent swimming, of course, is a sequential decision making. You have to keep making the right sequence of decisions until you don't sink and reach the other end. Okay, and in the beginning we keep sinking, and then we slowly reach. Now the question is, we are learning swimming, we are improving our performance. The question is, when you learn swimming, are you learning the transition function? Do you think we are learning transition function, or we are learning we're doing model-free learning. Okay, again, obviously, they say introspection is the worst form of psychology, and so we all are doing the worst form of psychology here, right? But I think so. And since you believe me and I believe you, I guess we must be right, okay? In general, basically, the question about whether or not something is model-based can be answered by saying, can I actually simulate in my head what would happen if I lift my hand like this, and I put my hand like this, and I put my leg like this in the water? Right? I don't know. This is part of the reason. In fact, one of the cute things that I have, again, these aphorisms that I make up for myself is, eventually most of the learning that we are doing will be, I won't have a job. But hopefully after my tenure is over, you won't need teachers because there'll be all these computers, and computers will be learning from computers, our computers, you'll be learning from the computers, whatever. But those kinds of things are great for model-based learning. I think if you want to be in the teaching profession and want to continue to have a job, go take up swimming instruction. Do you see what I'm saying? Try to learn swimming by watching videos. I tried, and I almost sunk. Okay, right? So anything model-based, essentially, you can simulate. You can get the knowledge and then simulate in your head and see what will happen. Model-free, you just sort of learn the right action to do without actually going through the intermediate step. So I would say that many of the physical skills are essentially model-free learning. Okay, now there was another question in the forum, which is everything related to swimming completely model-free? This lady who essentially tried recently to swim from, basically swim from the Keys to Cuba, right? I forgot, and now clearly if she had no plan whatsoever, right? After a bunch of time of swimming, she realized, I really should have asked some people to accompany me because I'm now sinking and nobody is there to find me. See, she did plan. She planned to have people around to go along with her, okay? But she didn't plan how exactly am I going to put which hand what time. Okay, so what happens in many of these cases is at a certain lower level you may be model-free, but higher level you again become model-based. Okay, but anyway, skills, for example, you want to learn using model-free techniques, and that's one reason why learning model-free techniques is useful. Okay, now why does this actually happen? We know that swimming has this problem that we probably can't think of learning it in a model-based way, but why exactly? And one idea would be, what?
Actions are stochastic.
All actions are stochastic. The entire MDP actions are stochastic. So if you just say that everything's stochastic, you must learn model-free, then why do we waste our time talking about T? Again, remember, by going model-free, you're giving up something humongously important, which is the ability to predict future just by thinking. Right? I don't know exactly, I'll throw this in. How many of you know, just right away answer my question, how many of you know where W is on the keyboard? Right away. The best way you'll figure it out is by hands. Because your hands know, your head doesn't know. Right? Okay, now thankfully for this you can simulate. Your hands, this is where actually the advantage of simulator exists. Okay, whereas if I ask you the same kind of question about swimming, you need to simulate swimming, but we don't have good simulators for swimming unless we have at least some water. Okay, so in essence, if you don't have T, you have inability to think about the future. And so if you're doing model-free learning, you're taking a hit. And it must be because there is some advantage for doing it that way. And there is a huge disadvantage in trying to learn the transition function. And partly, normally, that can happen if the transition functions are huge. That means any action can potentially take you to huge number of states. Okay? And that's kind of true in swimming, actually. Okay? It's basically depending on, first of all, the number of actions themselves are humongous. right? Because this is continuous, swimming is continuous, it would be nice to discreetly swim and then discreetly sink, right? But swimming is continuous, right? And so there are a huge number of actions, and each of those actions can get you to huge number of states. I realize that one small action is not going to suddenly take you to Los Angeles, but within the pool that you are in, you will get into huge number of configurations depending on what you did. You may actually go 1 meter forward, or you suddenly sink, or you wake up, say, kind of gasping for breath. All of these are possible. And rather than learn all those steps, you say, to heck with it, I'll just learn what's the right action to do. Okay, so that's sort of an approximate reason, a motivation as to why people, why we wind up learning about model free reinforcement learning. Okay, so that's the reason for model free. And then have we seen model free reinforcement learning until now? Of course, today I already kind of made this point multiple times before, but you know at least one model free reinforcement learning technique now, right? Which one is it? Monte Carlo. The very first one we did is model free because it didn't care about T. Okay? But I'm going to tell you another one. And as I tell you that, which is sort of more popular in the reinforcement learning community, as I tell you that, you have to keep thinking about how does it compare to Monte Carlo learning. And then I'll answer that a little later. Okay? So one model free learning basically is called what's called the temporal difference learning. Okay? And now this is model free for passive, by the way. I'm doing passive model free learning first. Okay? And then, so we're doing temporal reinforcement, temporal difference learning. The idea is, again, because it's passive, the policy is fixed. Okay? And you are trying to get the value without actually computing the transition function. And all TD basically says is take an action. So just basically it's an experience issue, right? Take an action, will get you a new state, and you get a reward there. Okay, so currently you are in some state, at any given point of time, this is you're doing experience, right? So you are in some state S, and currently your approximation for V of S is known anyway. And then you decided, the pi, the pi of S tells you do an action A. Pi of S basically, because you're following your policy, it tells you what action to do. Okay, so you did that action. Now, when you do this action, in real world, you get exactly one state. You don't get sets of states. You only get one state. Okay, let's say you got S1. Now you do know what is the current, what is the current approximate value for S1. Right? You do know that because basically you start with an initialized value function. Let's assume all of them are initialized to 0 except for ones which have rewards which are initialized to rewards. Okay, and then at some kth iteration, you basically have the current estimates of value functions for everybody. And then you went from S to S1. Okay, now think about the following thing. Suppose your current estimate of V hat S is minus 10,000. And you did this action A. You came to V hat of S1. Let's say the current estimate of V hat of S1 is plus 100. Clearly, this can't hold, right? How can you have real rich neighbors and be so poor? Not getting into politics, but how do you manage it? Okay? And really, it cannot be minus 10,000 if in fact you have an action to go from here to here. So in some sense, if you really have rich neighbor, then maybe your current estimate is kind of bad. And you need to sort of change your estimate to be more in tune with your neighbor's estimate. Now you might say, well, maybe what if neighbor's estimate is wrong?
Yeah.
That's fine. But then some other time that you come here, Okay? So this is actually the way, in fact, one way you can think of doing, and in fact, for some cases, that's what happens in spreadsheets. This is how spreadsheets can work. Every spreadsheet cell looks at its neighbors in terms of the formulas that constrain it with respect to those guys. And since these formulas may not be evaluatable if you don't know all the neighbors' values, but since you do know the current values of the neighbors, you can update your value. It's just that this iteration can be done very fast. Okay, so in essence, temporal difference learning, all basically says is if you think it is minus 10,000, your policy is telling you must do actually A here, and then you get to 100, a state with 100 actual value, then maybe you really should improve. You should change your estimate to be a little more positive. Now, how fast am I going to do it? How fast am I going to do it depends upon some damping constant alpha. Okay, and that's basically the rate of learning. If your rate of learning is very high, then in essence you believe completely your neighbor and not yourself. The rate of learning is very low, you believe your current value more and your neighbor's value less. Okay, so that's basically what you do in temporal difference learning. So you nudge your value in the direction of your neighbor's value, okay, by a factor alpha. Okay, so you have minus 10,000 here, and then the difference between minus 10,000 plus 100, and you take an alpha of that, add it to this guy. And that would make it a little more positive. Okay? Right? That's temporal difference learning. Any questions? And again, the question, of course, that you have, one question that you had was, what happens if my neighbor, two things can happen. One is this action, there are two ways in which the whole thing is going to, whole thing can become wrong. One is this action A has a 10 power minus 7 probability of actually getting you to S1. But in this particular time, you just lucked out and you got S1. And the second is the current estimate of S1 is very far away from its true value. In both ways, this backup is going to be wrong, but only temporarily, momentarily. Because as you keep learning, as you keep visiting states, this thing will all even out and everybody learns their correct values. Okay, that's temporal difference learning. A cute idea. Okay? Yeah, so I don't know, you can do an example, but I think my example is better. Essentially you have two values and you're essentially nudging yourself in terms of towards your neighbor's value. Okay. Anybody wants to say anything about how this connects to Monte Carlo? Yes?
So Monte Carlo, you only get your predictions for the values at the very end. Once you've run all your Monte Carlo, you can then...
Actually, it's not necessarily true. It's basically, remember this, even Monte Carlo does go through the states. You are experiencing these states. So as you are going through those states, you keep getting dings, R pluses.
Okay, I was going to say that this seems to be more dynamic.
Yeah, so the point is, first of all, you have to realize that there is some obvious connection between this and Monte Carlo, right? Okay, so since we brought that here, I actually kept changing my term, my mind as to whether right after this, should I talk about the connection to Monte Carlo or later, but I kept changing the position of the slides, but now I changed my mind one last time, and I'm going to do that first. Okay? I would say, essentially, it's a question of how you are using your experience. How you are using your experience. Okay? Eventually, so this guy starts from this state, does one action, gets a state, and you can do backup right away, based on the next neighbor. Okay? Or you can go 2 levels down, back up. 3 levels down, back up. When I say levels, it's not search, it's actually experiencing these states. It's reinforcement learning. You are experiencing these states. Okay, so the idea is, in temporal difference learning, you started from S, you did whatever the action is supposed to be done there, you got to S1, and as soon as you got, you basically just right away are trying to update your value based on your neighbor's value. And then when you go from here to the next guy, this guy updates the value based on its neighbor's value. But very equivalently, what I could have done is, let me go do A, get to S1, and then go next. Pi of S1, let's say, gives me A2, so I do action A2, and then I will get S2, and then I have the value for that S2. Now, S2 is just as much of a neighbor to me as S is, as S1 is. I can push my value towards this too. Do you see what I'm saying? Okay, with a slightly different landing constant, you could push your value towards this too. And it has some advantages, some disadvantages. Advantages are, if there was like a minor mistake here in going through this, then you avoided that. And you took, so basically here what you would do is I'll only take the reward in terms of gamma times the reward here plus gamma squared times the value of this state. That's how I use both of these. Okay, as again as just directly using the value of this state. By doing this, I can make up for any minor errors on the way. But on the other hand, I'm waiting longer before I update my values. Okay, so in general, you can think of this in terms of n-step returns. TD learning, temporal difference learning, is a one-step return. So you just do one action, see what, and then right away change your value function based on that one step. Okay, and then you can do 2-step return, you can do 3-step return, you can do n-step return, and then you can do Monte Carlo. And Monte Carlo can be essentially thought of as infinite step return. Just basically what you're doing is you keep going until you hit some, you keep going just forever, or you keep going until you hit a terminal state. The advantage of a terminal state is once you're in the terminal state, then from then on you will be in the terminal state. Okay, and since it is IID, this is infinite horizon Markov addition processes, all these things are going to sum to finite quantities. Right? Okay, and so the real question is whether I want to do Monte Carlo return, n-step return, 2-step return, 1-step return. And the trade-offs, as I said, is how fast are you going to learn? Okay, versus it's not so much that I don't get any feedback. I do get feedback right after one step, but I'm less likely to believe it than the feedback I get k steps later. And this is where actually people who did 471 last semester, I can give an example, which makes a lot of connection. Remember the game trees, okay? In the game trees, essentially you are at a particular board position, you're considering the actions you can take, and then you can get the board positions and you're evaluating them directly. If you have an evaluation function, you can evaluate them directly, do min-max, just one level up. Or you can extend this game tree multiple levels, apply the evaluation function at the lowest level, then do min-max alpha beta pruning to actually find the backed up value. We talked about the advantages versus disadvantages. The deeper you go, the backed up value is more likely to be correct. But it takes more time for each update. That's the same situation here. Yes?
So would it be the case that the temporal difference learning would actually be easier to parallelize than the Monte Carlo learning? Just because each step is kind of more discrete? So you can have a bunch of processes.
No, I don't quite know what parallelized means, because in general, essentially, unless you can clone the agent,
Well,
You can, unless you can clone the agent, what does it mean to parallelize? Basically, again, the thing that I want you to understand is this is actually experiencing the world. So I cannot have, it's always easier for me to learn if I have 8 copies of me sitting in 8 different classes and I figure out which of them is going well and then go to that class, right? But that's not possible. In search it is possible. If you have a simulator, it may well be possible. But if I have to act in the world, unless I can get somebody to act on my behalf and they have no life of their own, I'm basically stuck with. So the word parallelism in reinforcement learning doesn't make too much. I mean, at least the normal reinforcement learning. You are the only agent. It's just a question of how quickly are you changing your estimate of the value of the state. Are you going to wait, or are you going to right away update based on just one step?
So let's say that I'm the agent,
Mm-hmm.
and I decide I want some coffee.
Mm-hmm.
So I walk up and I drink some of that coffee.
Mm-hmm.
The question, or the difference between the temporal difference and the Monte Carlo, is in the Monte Carlo, I would then continue on and do other things until I reach some sort of sync state, or until I die, basically.
Yeah.
And then I say, maybe I shouldn't have drunk that coffee.
Yes.
Whereas the temporal difference, after I drunk the coffee...
At least for a while you think this was a good thing to do. That's correct.
Okay.
That's completely
And the
correct.
temporal difference, I would reevaluate that directly after drinking your coffee.
Yeah, and then but you update that eventually. In the sense, as you continue on, if you then find that you will get failed in the class if you drink my coffee, right? Not that it's true, but suppose that's the case, then you will find by the end of the semester and update what's the right action to do from that state. I mean, what's the value of the state action pair of you going from the state you are in to doing the drinking my coffee action.
So every time I take an action, I evaluate the results of that action and update the value of the previous state.
Exactly. Whereas n-step learning, you update only after n steps forward. Again, reinforcement learning is just chock full of analogies to real life. And sometimes that can get into the way of understanding probably, but I can't avoid doing the analogy. One other, since you're into drinking stuff, one of my very favorite Far Side cartoons. How many of you know Far Side, the cartoons? Okay. One of my very favorite Far Side cartoons is these 2 guys are basically like disheveled and they're basically walking in some Sahara desert. Okay. I mean, essentially they're completely, thirsty and they're about to die. And they suddenly see a little tap in the middle of the desert. The first guy starts running and then opens the tap and starts drinking. The second guy is saying, hey, wait for a second, let the water go for about 15 minutes, then the cold water will come. Right? I think it's kind of connected because essentially, of course, one way of making sense of that is that this guy is an eternal optimist, compared to the other guy. But, he's doing for an n-step return. And on the way to n steps, you might actually die, in which case you may not get to do any return. Okay, but if in fact he did live, then he would have been a happier guy because he had cold water compared to this other guy who had hot water. And presumably hot water is not as good as cold water if you are in desert. Okay? Anyway, so that's about n-step returns. And there is even an interesting, in fact, these pictures here essentially tell you how the RMS error, how the error in the values estimated change. Okay, for different values of alpha, which is the different levels of the rate of learning, okay, and different number of different step returns. This is the 15-step return, this is the 1-step return, this is the 5-step return, this is the 60-step return, and so on. Okay, so for example, it's basically saying, if you're using 1-step return, then as if alpha becomes higher and higher, then essentially you kind of, your RMS error kind of slowly comes down and then starts going up. All of them, RMS error goes down and starts going up as the alpha increases. Okay? But then the minimums occur earlier for higher step, larger step returns, larger value of s. Make sense of this. Look at this and make sense of this. But that's one, you can actually you have pretty good intuitions, I think, being just human. as to what n-step returns will be doing. And we actually specified what I'm going to do here, right? Because I'm going to consider my sample to be gamma times R of S1 plus gamma square times V of S2. That's my sample. As against in the normal temporal difference learning, in the normal temporal difference learning, the sample is just the R plus gamma times SH. Okay. One other thing that I want to mention is this is further thing, but this is the n-step return. This itself makes you connect Monte Carlo to one step. The other idea is something called TD lambda, which essentially says you can average the returns. Instead of just doing either 5-step return or 4-step return, you can do an average over 1-step return, 2-step return, 3-step return, all the way to 10-step return. And you do a weighted average over these such that they'll all add up, such that the weights add up to 1. Okay, and if you do this, you essentially have TD lambda. Okay, so in my game tree analogy, essentially I'm trying to figure out what's the best action just after 1 level, and then I keep that in mind, and then what's the best action after 2 levels, and then what's the best action after 3 levels. And I'm sort of taking, instead of actions, I can also talk about backed up value. And I'm taking the backed up value average, in essence. Okay, and again, I won't go too much into detail here, but that's another way of connecting the depth of your experience. How deep are you going? Okay, and then either you can decide upfront everybody goes to a particular depth, 15-step experience, or you can say 1 to 15, and I take averages of the returns from all of them. That will give you TD lambda. That's a very interesting idea too, but I just want to mention that here. So as far as I'm concerned, if you understand TD, that is normal 1-step return, temporal difference, and Monte Carlo, that's good enough. But this sort of puts everything in perspective, that there are multiple ways of getting your return. Yes?
So looking at the actual value equation you had given us a couple of slides ago, that value equation won't change depending on our step value, will it? It's just when we go back and evaluate it?
Yeah.
Okay.
Yeah.
So it's constant regardless of what value for K we take.
No, because what happens is, so here, I think. Okay, so if you just went 1 step, you take the reward for the transition itself plus gamma times the value of S dash.
Mm-hmm.
If you go 2 steps, then you take the reward for the first transition plus gamma times the reward for the second transition plus gamma square times the value for the second state.
Wouldn't that be taken into account when we recalculate the value for the second state, though?
No, I'm just talking about how to do this for each state is only updating based on 2-step look ahead. Okay?
So that's K equals 2.
Yeah, that's K equal to 2. Not,
Lambda
n equal to 2. Not lambda. Lambda is different. Lambda essentially takes both the 1-step and the 2-step return, takes the average of them.
Root means what?
It takes average of those 2 experiences. Any questions? Okay, one other thing I want to mention, since we are already so deep into this, is this picture. So essentially, okay, so one of the dimensions that you want to think of, we talked about dimensions of reinforcement learning. One is model-based versus model-free. Okay, that we understood that clearly. The other is passive versus active. You understood that too clearly. And then a third dimension that sort of became obvious based on the discussion we had today. And in fact, let's see. I had shown this slide in the very beginning last class, and I just skipped over it, saying this part is hard to explain at that time. But now we can explain this. The extent of generalization, so not the extent of backup, the types of backup you are doing in using your experience. And so here is a nice little picture. You have on one end, on this axis, you're talking about sample-based backups. On this axis, you're doing full backups. Okay? Sample-based backup means you actually execute in the real world and then only look at the state that you encounter or the sequence of states you encounter, and using just their values you back up and recompute your value. That's here. Okay? This side. And then the other side is full backups. You don't just consider the state that you see, but you consider all the other states you could have gotten into. And then use real Bellman backup. Okay, so now the interesting thing is, first of all, you have to realize, why would I be here versus here? Clearly, if I do full backup, the backup cost is higher. But then it can't even be done unless I have
transition function.
yes. We're making progress. Okay. Unless we have transition function, we can't do full backup. Right? Okay, that's a lovely point to remember. So if you are model free, you are stuck here. You're only stuck in this level. Model based, you can do this. You can also do this if you don't, You can have the model and decide not to use it. Right? Then you can do that. Right? Okay? So model based, either here or here, model free only here. Okay? And then the other interesting question is the depth of lookup. Okay? The depth of lookup, temporal difference learning is, if you decide on a sample, then how deep is your sample? Temporal difference learning just does one transition and starts back. An n-step or a Monte Carlo goes all the way until it dies, or basically reaches a sync state and then backs up. Notice, of course, that in fact, if you are reaching a sync state, this better be done on the simulator, because there is no you to back up if you die. Right? Okay? So, Monte Carlo is on this extreme, as deep as you can go. Temporal difference learning is here, which is basically one-step learning. And the TD lambdas, the 15-step learning, they are somewhere in the middle. Right? Okay, now the interesting question is, what happens on this side? You could do deeper versus shallower here too. There is no reason to do Bellman backup only against the against the immediate neighbors. In fact, there is a technique called RTDP, which in fact looks suspiciously like game trees. Real-time dynamic programming. And the idea essentially is you start from the state, okay, you consider all the actions you can do, and for each of the actions you consider all the states that can happen. Okay? Okay, now if you stop right here and you take the values of this and you take the expected value at the action level and take the max over the actions and consider this to be the value backed up, you're doing one-step Bellman backup. What if I have time on my hands? I go from each of these, I go expand again. So from S1, I can, let's say, do 4 actions. I can do, here is one action, here is another action. Maybe only 2 actions I can do from S1. And then that will get me to this state, this state, this state, this state. Okay, in each case, at the action level, it is AND. That means you need to consider both states happening. And then at the state level, it's an OR. You just need to pick the best action that will give you the best backed up value. Okay, so now if you do further down here, then you apply the value function here, and then do expectation, maximization. Expectation, maximization. That's just like min, max, min, max. Except in game trees, instead of doing expected value, you consider minimum value for your opponent. Here essentially you can think of MDPs as a game against nature. And the assumption is nature is not out to get you. Okay? Nature is not even aware of your existence. It has some probabilities and it's just basically going to do the outcomes of the action unbeknownst to you whether or not you're a lucky person or not lucky person. Whereas your opponent with a brain is not likely to be that. They are essentially going to do the thing that will cause the most damage to you. So if in fact there are two board positions and this one will give you -100 and this one will give you +7, your opponent, you can be sure, will with one probability 1.0, pick this. Because that will cause you the maximum damage. So you do min and then take the max. Just a second. Whereas if you in MDPs, you say this is let's say you say this is 0.01 and this is 0.99. And so you actually say, since nature is not out to get you, you multiply 0.01 times -100 plus 0.99 times 7, and that's the expected value of this action. And you still take the max over the expected values. So min max versus expect and max. Yes, sir.
Kind of slightly elaborate question. This exhaustive search seems like we could have used that in the case that we fully knew the T and we fully knew the reward.
Yeah.
So, but we didn't cover this when we we're going over MVP. So I guess why would we use exhaustive search if we didn't fully know?
So the reason we didn't cover this is actually a beautiful question, and we will do this because in essence, one of the crazy things, there's an elaborate answer. Bear with me. First of all, his question is something like RTDP, something like what I'm doing here. Why should this be only done when you don't know the T and R? Why can't you do it even if you know T and R? Okay? And instead of doing the pure value iteration and pure policy iteration, why can't I do this to do real-time decision making? Okay? In fact, one of the interesting things is for the longest time, and even now for people, essentially some of them think reinforcement learning as just approximate ways to solve known models. Okay, so here is this is the way to think about this. So suppose I tell you, here is a little thing to do, here is a little task to do. Here is, 2-mile high manuals which tell you exactly how to do this task. Read this and do it optimally. That's what your boss said. What do you do? Say, who the heck reads the manuals? Right? I mean, the RTFM wouldn't exist if in fact people read manuals. What do people do? Well, just wing it. We'll try stuff and then figure it out. And so we'll slowly figure out what's in the manual ourselves. When you did that, you had the model and you still used reinforcement learning. Our reinforcement learning like thing. When you do have a model and you do this, in some sense, simulator is free, essentially. Okay, so the answer to your question is when we come back to MDPs, so I don't know when we'll do this, but there are two things I still want to do in just the pure inference issue. Okay, and I did not do it right away because they're connected to this, essentially. Because some techniques can be both seen as just inference techniques or learning techniques, or both. Okay, in the case of RTDP, when you come up to here, if you actually have the model, right, you don't need to, you can just do this in your head. You can do the entire tree in your head and just back up in your head. And you'll never die because you're doing it in your head. Okay, and the only reason you will do this is the underlying MDP is so big, it has so many states and so many actions that trying to do full value iteration and full policy iteration and then getting the optimal policy and then start executing it would kill you. It's like you're in the middle of rural road or Mill Avenue and you're trying to sort of make a decision as to whether I should duck to the left or right, given the oncoming traffic. And if you try to compute, an offline big computation of the optimal policy, you'll die. So what you need is an online decision. Right then and there, what's my best option? That's what you do here. Notice that in fact, the min-max game trees that we do in chess, etc., are they using, so I connected RTDP to min-max. That's what I did, right? But RTDP, I mentioned RTDP from the point of view of reinforcement learning. That means doing a bigger full backup. Go further down and then back up. Right? But then this is reinforcement learning, so if I don't tell you anything else, you have to assume that I will experience each of the state I go through, where I'll get my dings for my rewards or my, pats on the back for my rewards. You see what I'm saying? And the last state, if it is not, if it is terminal, then the reward is basically what I'll keep getting. If it's not terminal, then essentially I'll take the current estimate of the value. That's how I put RTDP here, but then I connected it to min-max, and min-max is done with full model or without full model?
With full model.
Do people play chess with full model or without full model?
With full model.
Actually, most of you play chess without full model. Again, because it's so big, how the heck, why are we going to get the time to read it? But if you decide not to read the manual, it's not my mistake. Okay, do you understand what I'm saying? I gave you the manual. If you don't read it, it's your mistake. Okay, so chess is a case where you have full model. It's just that reasoning with the full model is so hard that, in fact, finding even if in fact if you're playing chess against nature for once, instead of actual opponents, then you will need an optimal policy for chess, optimal MDP policy for chess. Why would you want to compute the entire optimal MDP policy? What you really need to do is make a decision before before the actual inevitable somebody else's turn comes. So you do this idea. Essentially, what you're doing here is online. What you talk about here is online decision making. That means as you are executing, you are also deciding your policy. The whole MDP discussion we did earlier was offline decision making. You make the optimal policy, then you start executing. Sometimes like in real world, when you don't have the model, you can only do online. And just hope asymptotically you will learn the optimal policy, which would have been the policy you would have learned even if you had the entire model up front. Sometimes when you are lazy and you do have the full model, you still do online decision making. Then it looks just like reinforcement learning. Except instead of acting in the real world, you just simulate what happens because you have the model. That's a great connection. If you understand this, you are way ahead in terms of understanding how reinforcement learning and MDP literature connect. In fact, the idea of from operations research side, reinforcement learning is just called approximate dynamic programming. That's all. Just called approximate dynamic programming. As if you have it, so it almost looks as if you have the model, but you decided to go with the approximation rather than the full convergent version. In RL case, you cannot do anything more than approximate, but even if you have full model, sometimes to make your life simple, inference life simple, you might decide to do the Cliff's Notes version of the full textbook. How many of you actually read textbooks? Yeah, so he's a good guy. Okay, but many of you actually don't even read the paper in the exam time because that takes valuable time away. Just start answering, quickly. Right? That's basically what you're doing. You're doing online decision making and you're learning the model as needed. Okay, and it's a reasonable thing. But anyway, so if you just stick to the reinforcement learning, view, then you could have done deeper full backup versus deeper sample-based backup. Now, we did not talk about this in any of the reinforcement learning algorithms, but RTDP would be one. Okay, and then there is also, just as there are points here, there are also points here, there are also points here. A point here would essentially be actually called Monte Carlo tree search, where you in essence do multiple samples. Rather than a full tree, evaluation, you do multiple samples, starting from the state, one sample, one more sample, one more sample, and then take average over there. That's a way of doing reinforcement learning. Okay, so what we did is we learned two easy algorithms, and then we learned the entire, we sort of tried to get an idea of the world of algorithms around it. That's what we did. Any questions on this? By the way, that's a very good question. And you should think about, if you don't understand the question, first make sure that you understand the question, and then understand the answer. Okay. Okay, so what I'm going to do next, before I end 10 minutes time, is I'm going to do active model free learning. Active model free learning. So I want to basically do something like temporal difference or any other model free. Temporal difference or n-step backup or Monte Carlo or TD lambda. It doesn't matter. I just stick to TD right now. Okay? And I want to do active learning. That means I'm not given a policy. I need to figure out the policy as well as the value function up front myself. So clearly you have this issue of exploration. That's fine. But there is another bigger issue. If you don't have a model, if I just give you the value function, how do you convert it into a policy? It's not a bigger issue, but it's a technical headache, right? So I know this, I know that this neighbor is rich, this neighbor is poor, this neighbor is sadistic, this neighbor is masochistic. I know all this stuff. So what should be my action? I don't know what my actions do. Model is not there. Do you understand what I'm saying? Model is not there. So what if I try to basically do action A1, is it going to take me to this neighbor or this neighbor? With what probabilities? I don't know that. If I know this, I had no problem. I essentially computed expected backed up value for each of the actions and took the max. Under the guise of model free learning, I basically lost T. And so I don't have a way of figuring out the action. So the interesting question is there a way of figuring out the action without actually giving up on the model freeness and going back all the way to T? We do know that if we know the T, we can do this. The question is, can I have done it without knowing T? And that's where the Q values come. What I'm going to do is basically, rather than just have a value for each of the states, I will find the best value I can expect for each of the actions done from that state. And the expected value I can expect for each of the actions done from that state, not best. Actions, once you do the action, they'll do what they're supposed to do. Okay, so if you look at this picture, this is like your grid picture. Previously, what do you think you would have remembered as the value here? Wake up. What do you think you would have remembered here? If this is some 4-valued thing, but these are basically this, what we are trying to say is if you try to do the go down action in this state, the expected value is 0.54. If I try to do go right action in this state, the expected go left in this action in this state, the expected value is 0.43 and so on. Okay, now the point is, so that means there are as many Q values, these values are called the Q values. There are as many Q values as there are actions. Okay, so for any given state S, I have QSA values. Doing action A in state S, what is the expected value I get? My current estimate of what is the expected value I get. And if I now want to know what is my estimate of value of S, what do? Take max over A of Q of S. That's it. Right? if I have 4 actions, so going back to my neighbors, my sociopathic neighbors case, so if I don't know the transition functions, but I happen to basically have estimated the Q values rather than the values. And my Q value for doing, basically go right from my home action has the estimated value of 55. Q value for going left from my home has an estimated value of 65. So all of a sudden I already know between these 2 actions the 65 one is better. So I'll pick that. Do I know what are all the states this action would take me to with what probabilities? No. So I don't know the model. So all I did is, instead of remembering a V of S function which is of size S, I'm remembering a Q of SA function which is of size S times A. And then I'm computing V as needed. You do realize that. Once I do have the Q, then I can compute V. With this little extra bookkeeping, you can now do active reinforcement, even though you don't have the model. Yes, sir?
Sounds like an almost completely explorable
What?
completely a method that's a technique that's almost completely dominated by the exploration side.
No, the exploration is orthogonal to this issue, by the way. Exploration exploitation has to be still done. If you have active learning of any kind, you need to do exploration. All I am saying is, previously you were just interested in learning the transition function and then converting it into the value function. Okay. Now you're going to just learn the Q function, and then passive would have just learned value function, and then you won't know what to do with the value function. Okay, talk of far side cartoons, the thing that suddenly comes to my mind is this one cartoon where the cows are at home and they have the phone ringing, and the one cow looks to the other cow and says, "There goes the phone again, and here we sit like stupid people lacking opposable thumbs." Now, I'll let you think about why did they even have phones in their home when they didn't have opposable thumbs. But essentially, you have the value function in front of you. But because you don't know what action will get you what value, you can't do a thing. And the Q function will let you basically retrieve the best action without knowing the transition model. That's why it's Q. Okay, that's it. And so basically you do everything like what you did before. So this is my last slide, and I'll come back and do it next time if you want. But essentially, I'll remember the Q value. I'm keeping track of the Q values, and so I take, whenever I have when I do an action and I get a state, then I have the ability to update. I did action A from state S in the current sample. So I have the ability to update just Q of SA. And it should be nudged towards the Q value I experienced by going to that action, by going to that state. So I'm still doing the same thing as temporal reinforcement learning, temporal difference learning, except previously it used to be V plus alpha times sample minus V. Now it is Q plus alpha times sample minus Q, where each of the Q values is nudged towards its correct value. And everything else remains the same. And the exploration stuff is still thrown in too. And that's Q learning. And the Q point you want to remember is you got the ability to decide what action to do. Because in active learning, at every given time, you need to be able to convert what you have into the policy. If you have the Q values, you can convert into policy. If you have transition function, you can convert into policy too, but you don't need the transition function. You can get by with just the Q values. And Q values are only A times bigger than the number of values you are remembering. That's the cute idea of Q learning. We'll stop here. Okay. Ask me questions about this. Most likely next class I'll mostly take any questions you might have about Q learning and then move on to the next one.